Hello, I'm Professor Stephen Abbott. Welcome to the second of 4 videos on IGC, inverse gas chromatography, what it is, what it does, using my apps. As explained in the first video, I'm very grateful for the help from AdScientists in preparing these apps and these videos. You can find the apps themselves on my practical chromatography website, and they're all free and run on all platforms. We explained in the first video that IGC works by having your test material, fibre or powder, coating, in a GC column, and you inject different known probes like hexane or toluene or methanol, and you measure the retention time, Tn, and from that you calculate a value of Vg, and then delta G, the free energy of interaction. Refer to the first video if you are not certain what this means. We discussed in the first video just measuring dispersive energy. You just have the peaks from something like pentane, hexane, heptane, and octane, and from the slope of delta G versus carbon number, you can calculate the dispersive free energy. We can do something a bit more exciting if we do the same experiments but add one other type of probe. So we know that delta G is RT log n Vg, and we can calculate a morphology index, IM, which is the Vg measured from a branched alkane to the Vg of that same alkane if it were linear. What does that mean? Well, you have to have a topology index, chi-t, which tells you what effective length that branched alkane is. So once you know the real Vg of a branched alkane and you know its effective Vg, then you can calculate this morphology index, which tells you how rough it is. Because if you have a rough surface, a branched alkane is less able to contact the surface, and therefore the effective Vg will be less. So the morphology index is going to be less than 1 for a rougher surface. So we take something like 2-methylhexane, and although that's a 7-carbon alkane, which might behave like heptane, it actually behaves like 6.8ane. So you have the standard set of experiments, and I've got the same data as in the previous slide, and we find that the morphology index is 6.8, so we have that here, and suppose the Vg of the probe was, let's say, 4.3. Then we know that this alkane should behave as if it had a delta G of 5.3 because it's a 6.8ane, and if it had that, then we know the surface would be perfectly smooth. We know the delta G of the probe in reality, we know the delta G of what it should be on a smooth surface, and because this is lower, we know that the morphology index is 0.6. So this is a relatively rough surface. If we had an even lower one, the morphology index would be 0.4, and if it came out identically, then we would know that it was a smooth surface. The morphology index is 1. We can do a similar experiment, not just with an alkane, but with something like, for example, toluene. So we can then get a specific interaction parameter, ISP, which is the ratio of the delta G which you get from that probe compared to the delta G had that probe been an alkane. So again, we need a topology index chi-t, and we know, for example, that toluene behaves like an alkane with 6.3 carbons. So let's see what happens. We have the same experiment. The toluene should come out here at 6.3, but we're saying that in fact the Vg is 9.4, which gives a delta G of 6.1. So it's out here rather than that, and therefore the difference in free energy is 1.4 kilojoules per mole. So we know there's a specific interaction between toluene and the surface of 1.4 kilojoules per mole. What does that mean? I don't know, but the point is you do the same experiment with other probes like chloroform or acetone or ethanol, and in each case you will find a specific interaction energy of kilojoules per mole, and you'll be able to develop a rather good understanding of what's happening at the surface and what the specific chemical functionalities of that surface are. Again, a powerful technique. Many of you will know of acid-base analysis. The app doesn't do it here, we don't have a simulation of it, but by using specific probes with acid or base functionalities, you can disentangle the acid-base constants of the surface. So in this second video, we've seen how to get to some interesting surface properties by very simple experiments with a fundamental analysis.